Alright, so in lesson 4.3b, and again this is the last lesson in this unit, we're going to first look at y equals 1 over x. Talk about what that graph looks like. We've already actually talked about it today, but we'll talk about it again, because there's some extra information that you need to know. So this is the graph that we're discussing right now, that inversely graph. That's 1 over x. Now, why does it not touch the x and the y-axis is what we need to know, because that's what makes it inversely, right? Because it doesn't touch the x or the y-axis, it stays totally in two of the quadrants. That makes it inversely. Well, the key here is that there's a reason it doesn't touch the x and y-axis, because there is an imaginary line vertically and horizontally that it's not going to touch. And it just tries to get up close to it. Think about it. 1 divided by 2, 1 divided by 3, 1 divided by 4. Those numbers are getting smaller, aren't they? When's that going to get 0? Never. Because the only way the answer ever divides to be 0 is 0 is on top. 0 is not on top. So it's going to get smaller and smaller and smaller and get as close as it can to this line, but it's never going to touch it. Now, the vertical line is called a vertical asymptote. A vertical asymptote is an imaginary line that your graph can hug up next to. It's caused by what makes the denominator 0. A-S-Y M-P-T-O-T-E, asymptote. So this vertical asymptote is what makes the denominator 0. I guess that's 0. So that's why it's going through the x-axis through 0. Huh? It's an imaginary line that cuts through the x-axis at x equals 0. Then you have a horizontal asymptote also. Stop talking. And the horizontal asymptote, for the problems that we're going to be discussing, the horizontal asymptote, there's a reason why it's where it is on this one. Now that line can shift, and once we start looking at the graphs shifting up, down, left, right, both of these lines can shift. But originally, the reason why the horizontal asymptote goes through y equals 0 and crosses the y-axis at 0 is based on the exponents in this problem. So let's talk about the numerator versus the denominator. The numerator is 1. That's a constant, right? What power does a constant have? Come on now. How many x's do you see? On the top? 0. That's because the power on the top is 0. Now in the denominator, we have an x. And that's got a power of what? 1. Because x means 1. Now, is that greater than, less than, or equal to when you compare the power of the top to the power of the bottom? Is 0 greater than, less than, or equal to 1? Less than. So when you compare the exponents of the top and the bottom, your horizontal asymptote will always be y is 0 before you move it up, down, left, or right, because it's less than. If it was greater than, there wouldn't be 1. If it was equal to, there'd be numbers in front. You'll learn more about that next year. This is the only one we have to learn this year. So that's why it was y equals 0. Now, those are numbers that the problem will never be. It can't be 0 in the denominator because that makes it undefined. It can't be 0 as a whole for y because 1 over anything is never going to divide to make 0. Now, let's talk about domain and range. Okay, with domain and range, because you have a vertical and a horizontal asymptote, there's one number it doesn't touch. It touches everything else. Doesn't it touch all the negatives? Doesn't it touch all the positives? But it doesn't touch 0. It does the same thing up and down. It touches all the positives going up, touches all the negatives going down, but it doesn't touch 0 either way. So today's domain and range work, I think we will use the fancy notation for domain and range instead of the interval notation because it's a little quicker and easier to figure out. Don't know if we've done the fancy with this class this year, so we'll see. Okay, this line reads, I don't just read the line, it's such that. So x such that x, and this funny looking e that looks like I squished it, okay, that reads is a set of. I left the word a out. Is a set of. So if I read it all the way across, x such that x is a set of all real numbers. That's what this capital R with the extra line is. All real numbers. Now, if you'd rather write all those words out, you're welcome to, but I suggest learning the symbols. It's a lot shorter. So x such that x is a set of all real numbers. But that's not really true, is it? All real numbers, but what? What number is it never going to touch? 0. So we have to make an extra little piece on the end that x cannot be 0. So when you do a domain or a range for a rational function, you put on the end what the vertical asymptote is, because it can't be that. And then for the range, you do the same thing for y. Y can't be 0 either in the original function. And so that's how you can tell the domain and range. Now I could do it with interval notation, but then you got to know more about how to write infinities. This is straight out, real easy. It's the same every time except changing the number on the end. So I thought we'd practice with this type of notation in this unit. All right. So those are the key features. That's all we need. That's it. That's all there is to it. So now we can introduce some extra numbers to the problem, and those extra numbers in the problem can affect the shape of it or affect where those dotted lines are. Or maybe it reflects it. Now we won't probably, unless we actually graphed points off the calculator, we will not see this compressing and stretching on this. And even if we did, we probably wouldn't even notice it. Because the stretching and compressing doesn't really show up real well if you're going to keep going next to those dotted lines. But what it does do when it stretches and compresses is it moves further away or gets closer to the origin right here at this curve. But it's not such a subtle change that you don't really notice it. So you can only really tell that sometimes from the formula, but don't see it on the graph. And then the other thing is the dotted lines do move around for the up, down, left, right. So knowing whether your graph moves up, down, left, right is important. And of course, every time you put a negative in the problem somewhere, it makes it reflect. Everybody agree? So we're going to have to figure out where do you put the negatives to make it reflect over the x or the y. So let's look at an example. And let's start with reflecting. I'm not going to change the top number because I only want it to do one thing. I want it to reflect. My question is, if I make it reflect, I don't know which way it's going to reflect, like over x-axis or over y-axis by putting a negative on a number. But doesn't always putting a negative at the beginning of a problem always make it do something? Was it x or y before? If you put it at the very beginning of every question. Like when you had negative x squared, did that make it reflect over the x-axis or the y-axis? Well, that made it go down, right? So didn't it go over the x-axis? Okay. When we had negative square root of x, didn't that make it go down below the x-axis? Well, let's see if this does the same. We put a negative at the very beginning of the question by putting it on the top, because the top's the first thing you get to. I could also write it this way and it would mean the same thing. My question is, if I do that, does it go over the x-axis? And if it does, then how do I look at that? So put that in y equals real quick. Now, after you do a couple of these, you'll realize you don't really need your calculator, but until you've done a few, you won't see what happens to it. So we're going to look at the calculator, see what happens, rough it out, and then we'll move on. So we're just adding a negative to the problem to see how does that make a reflection, because we know putting a negative times anything always makes it reflect something. So the original problem is always in quadrant 1 and 3. It's in 2 and 4. Okay, so what was in 3 went to 2 and what was in 1 went to 4, or did it go from 1 to 2 and, whoa, it could be either way, couldn't it? It's actually over the x-axis, but it could be either way and we wouldn't know the difference. So this negative reflects over the x-axis, we think. It did in all the other problems we talked about earlier. So I guess we need to figure out what makes it reflect over the y. Well, I don't know. Let's think about that. Because if it's going to reflect over the y, think about it. If it's in this quadrant, it moves to that one. If it's in this quadrant, it moves to that one. They're both in the same place. It doesn't make much difference, does it? It'll look the same. But how do we make it do that? Well, the only way I can show you how it does that is if I put in some shifting, because I can't show it otherwise. It won't be obvious to you. So I'll put a shift in this problem as well. Well, I guess we ought to look at the shift before we look at the shift within. Let's just look at a shift. Let's look at a shift, and then we'll look at a shift with a reflection. Okay, this problem is going to shift 2 different ways. Now, we're going to go back, and we're probably going to talk about domain and range here in a minute. But the domain and range of that problem is the same as the first problem, is it not? Think about that. Just reflecting, it did not change zeros, did it? So this one is not going to have the same domain and range. But number 2 has the same domain and range as the original problem that I did originally. All right, so let's look at this. So if you put that into y equals, make sure you put parentheses around the bottom. Now think about this origin that was between these two. Whether it's between 1 and 3 or 2 and 4 don't matter, but if you think about the origin here, that space in between here where the origin would be, is it still at the origin now? Or did it shift? How much? Or just what direction? To the right? Want to guess anything else? You got 2 numbers. It's got to do 2 things. Looks like it went 2 to the right and up 3. How come? Well, because we know this always gets set equal to 0, tells us to the right or to the left, right? And this always tells us if it sits up or down, and positive 3 means up. So whatever's attached to x always does the opposite, and whatever's on the end of the problem still does up and down. Now what did that do to my problem? Well, it did this. It shifted my vertical asymptote to the right and my horizontal up. Is that what your calculator looks like? See, that's the key to these problems, y'all. The vertical and horizontal asymptote that was on the x and y axis shifts to the right and shifts up or down based on what your problem tells it does. Now, let's talk about domain and range. How does that affect my domain and range? Okay. So the basic pattern for the domain and range is the same every time. The only difference is going to be the numbers on the end. That is going to be the only difference. Okay? So you're going to memorize these two domain and range patterns because they're real easy to memorize. And then you'll just have to adjust what number you put on the end based on the rules that I'm about to tell you. So this graph went to the right and 3 up. And that's what you're going to use to help you fill in the numbers on the end. See, the basic parent function are both on 0. But if you go to the right, what number are you on now? 2, because you went to the right from 0. So this to the right tells you whether to put a positive or a negative number sitting right here with x, because to the right's an x thought, right? It's not a y thought. And that 3 up tells you you started on 0 and you moved your horizontal asymptote up 3, so it's on 3. So it's real easy to get those two numbers. It's based on where you moved it to. And if you moved it left or down, you'd put a negative on it. That's how hard, it's not hard, it's just based on what the problem's telling you. So now, I want to take the exact same problem, but I want to make one change to it because we already know it does this. Okay? I want to make one change to it so that it does something else different, but it won't change the domain and the range, I don't think. I think it's just going to change the look of the graph. You let me know if it changes the domain and range. Change the inside of that parentheses around. If I plug 2 in that, is it still 0? Everybody agree? I didn't change the value of what makes it 0, did I? If I set 2 minus x equal to 0, negative x is equal to negative 2, x is equal to positive 2 if you divide by negative 1. You set that equal to 0 and you solve it if you don't know what the answer originally is going to be. If you went 2 positively, that'd be 2 to the right. And still 3 up. So I did not change where the vertical asymptote and the horizontal asymptote is. But I changed something about it. So, figure it out. What's the change? Did it change that I went to the right? Look at your graph. Does it still look like the graph went to the right and 3 up? What switched? Is it this way? So putting a negative on x makes it go over the y-axis, which is what we learned back when we first started doing this. Negative on x makes it go over the y-axis. Negative on the beginning of the problem makes it go over the x-axis. So this negative right here makes it reflect over y. And then I moved it to the right and 3 up. And this has the same exact domain as the last question. That did not change. What else can a problem do besides reflect, move up, down, left, or right? Translate. Okay. What do you mean by that? Okay, well that's what this is. Because the whole graph slid over, didn't it? I mean, this whole piece went over to the right 2 and up 3. So what else is there besides translate and reflect? Okay, I'm not going to do any rotating for this because that would make it really complicated. And this is supposed to be pretty simple. So what's the last thing? Dilation. So let's talk about what part of the problem do you think is going to make it change size? Well, what did I not change so far? The 1. Okay, let's change that. And to make it easy, I won't make it move anywhere. We'll just put a number up there and not put any add and subtracting in it. What if I have 2 over x? Now, for you to be able to tell the difference in that, we might have to look at it a little bit more closely. So I'll pull mine up here. If I put 2 over x versus 1 over x, whoop, and I'm going to bold the 1 over x so we can see it as the original. Zoom 6. So there's my 2 over x, and there's my 1 over x. Do you see what I meant about here's 2 over x? It's further away from the origin. This is 1 over x. This is 2 over x. It goes further away from the origin the bigger that number gets. So what do you think it's going to do if I put a half in there? That's right, it's going to get closer to the origin. And that's where your stretching and compressing comes in. It stretches it out more. It pulls it away from the origin. And when it compresses it, it pulls it closer to it. And so the same rules apply here that applied originally. The number on the top is greater than 1, so it stretches. Did I spell that right? Okay. Sometimes I look at it and it looks wrong. So if I wanted my problem to compress, I might would put like 0.5 up there. Now be careful. This is one of the things y'all got wrong on inversely on your worksheet. If the answer to K is a fraction and it's got a good decimal, you might want to put a decimal up there, because when you put a fraction up here, it has to sit on top. You can't bring part of it and put it down here. It's got to all be on top to show your K. So this one is less than 1, and this compresses. Now, we don't have to say compress vertically or horizontally, because it's not really compressing vertically or horizontally, but that's what it's doing. Now, does that affect the domain and range? No. The only thing that affects domain and range is up, down, left, right. Reflecting doesn't, and stretching and compressing does not affect domain and range. So the domain and range for both of these problems would be what we talked about originally, because there's no adding or subtracting in there to change it. So only adding and subtracting changes your domain and range to give you that sense of my vertical asymptote and horizontal asymptote are moving. So now that we see what everything can happen to a problem is, if the top's negative, it reflects over the x-axis. If the x is negative, it reflects over the y-axis. If it has adding and subtracting in it, whatever's it doing on the x, you set it equal to 0, and that'll be your left-right motion, and that's where your vertical asymptote moves to. If it has a number on the end, that's your up-down motion, and that number on the end moves the horizontal asymptote up and down. And now we've learned that the top number greater or less than 1 makes that stretch and compress work just like it did before. So let's look at some more examples with a little bit more involvement and talk about, you don't need a calculator to look at these, y'all. You really don't. You just need to know where those two lines are, and that's it, and whether it reflected or not. Is this number 5 or 6? 6. All right. What's the negative do? Reflects which way? Over x. Because it's at the top of the problem. All right, what's the 3/5 do? Correct. It's less than 1, so it compresses. What does x plus 2 equal to 0 do? That's right, 2 to the left, because it's going to be negative 2 when you solve it, because it's always opposite. And what does this minus 1 do? 1 down. All right, now let's see how that affects our graph. So how much did it move left or right? Well, it went left 2. So your vertical asymptote just moved left 2. So that means my vertical asymptote, we abbreviate VA. So my vertical asymptote always goes right or left. It shifts along right or left. So it went left 2. So it's x equals -2 is where that line is. Now, my horizontal asymptote goes down 1. Because the whole graph shifts down 1, the horizontal asymptote has to go down 1 from 0. So the horizontal asymptote is y equals -1. Now if you think about it, that makes sense. I was at the origin. If I had a point plotted there and went 2 to the left and 1 down, wouldn't I be at the point -2, -1? Well, that's what I'm doing, except instead of making a point out of it, because it's not a point, it's where the two lines intersect. Now, did my problem reflect? So 1 and 3 became 2 and 4. And I'm done. And I didn't need a calculator to do it. It's a pattern. Then you can state your domain and range. And again, it's a pattern. Whatever you wrote here is the two numbers you're going to write down there that it can't be equal to, because that's what these are equal to, and they're imaginary, right? You don't see these lines, they're dotted. Do you see them on your calculator? Well, let me rephrase that. Some of you might have an old version of your calculator, and it used to draw them in. Some of those 83s will do this, and it draws the vertical asymptote in for you, which was kind of nice at the time because it actually drew it in. But they took that part out when they redid the processors and did the 84s. So you just have to know that up, down, left, right motion tells you what number to put on the end here. So therefore, this one's going to be not equal to -2 and not equal to -1. It's that simple. It's nothing complicated to it. So you just go through and describe what each number does in the same order we've always described it. Haven't we always done reflection first? Haven't we always done compression and stretching next? Up, left, right, up, down. It's always in that order. It's just the left, right, up, down is very important because it tells you where these lines go. No, I'm going to make that minus. Plus 2. All right, 7 over x minus 4 minus x plus 2. Does this graph reflect? No? What's a 7 do? Stretches, because it's more than 1. Now, you got to set this part equal to 0. So if I take the 4 over and make it negative and divide by -1, I get positive 4. Is that right or left? To the right. What's this 2 doing? Up. Okay. So now, if I move my vertical asymptote, where did it move to? How much did x change? To 4. So your vertical asymptote is x equals 4. All right. Then that up 2 must be moving my horizontal asymptote up 2. Y equals 2. So those two numbers about up, down, left, right tell you what it did. And if it don't do both of them, then it stayed at 0. So like if I didn't have that plus 2 on the end, then the horizontal asymptote would be at 0. Because it starts at 0 and then it shifts. And then, did I have any reflection in this one? No? So I stay in 1 and 3. Now 7, that's pretty big. Am I going to be real close to this intersection or far away? Think that through. What did I tell you about that? The bigger that number, the further away from that intersection you want to be. So just put it a long ways away. And that shows you it's stretched because it got further away from this intersection. Now, I didn't do that real even because my graph's not real even, but that's kind of what it does. Alright, so when you do your domain and range, if you have listed your horizontal and vertical asymptotes, then you just take those numbers and throw them in there and you're done. Because what they are is the one number it can't be. Is this making sense to y'all? Is anybody having a problem with anything I've done so far in terms of understanding how to use each number out of the problem? And it's not that you can't look at your calculator, but the calculator really doesn't draw the vertical and horizontal asymptote in. That's why you got to know where to put it. I could plot a bunch of points on here with a table, but the problem is if I do that, I'm still not going to have those vertical and horizontal asymptotes in there without knowing that it moved around up, down, left, right. Okay. I'm going to give you all 3 to try. And I'm going to pause this video while you try them. But first I got to write them before I can pause it, right? Let me write them first. That way whoever's watching the video can do them too. Alright, so here are your 3 examples to try.